Welcome back, my dear students. Same fluid mechanics 18 CV53 fourth module A part orifices and mouthpiece second lecture. In this lecture we are going to cover derive an expression for velocity and discharge through orifice. Okay, this is a very important question for even examination purpose. Now look at here what they are asking. They are asking us to derive an expression through orifice. You already know in the previous class what is orifice. Orifice is a small opening, and now we need to derive expression for that small opening, expression of our velocity and discharge. Okay, now let us consider, write it down. Let us consider an orifice of diameter d and area A. Let us consider an orifice of diameter D and area A. Let h be the height of water. Let h be the height of water above the center of the orifice to free surface of the liquid, to FSL. Okay. Next, let us consider 2 points, that is 1 and 2. Okay, section 1 and 2. Now look at here what happens. Here water is stored and here a small opening is there, means here water will come like this, correct? This you can call water jet. Water jet is coming like this, and here if you observe at this particular point, what you will see, the water will come outside with this shape. Okay, this is the tank. This is the tank. At this point, particular point, you will observe this one, means little contraction will happen. Little contraction will happen, thereby area will be minimum. Area will be minimum. When area is minimum, then the velocity will be maximum. Because discharge is constant, therefore velocity becomes maximum. See, the first point is the area gets contracts, and the second point is area becomes minimum. The third point is where that area is minimum, that point velocity become maximum. And at that point, if you see the streamlines, all the streamlines are parallel to each other. All the streamlines are parallel to each other. Okay, such sections or such point at a particular section, we will name that one as a vena contracta. Vena contracta. Okay, they may ask you to define vena contracta. Define vena contracta. Okay, vena contracta is a section at the downstream side or at the discharge point where area is minimum, velocity is maximum, and all streamlines are parallel to each other. That section is called as vena contracta. We are very interested about that section, therefore the second point I will consider at vena contracta. Now look at here, this is a 2-2 section. Second point I considered at vena contracta. Right? Now wait. What after considering two sections? Usually we apply Bernoulli's equation. We will apply Bernoulli's equation. We'll write apply Bernoulli's equation. Where? At 1 1 and at 2 2. But at 1 1, if I apply Bernoulli's equation, then I will get P1 by rho g plus V1 square by 2g plus Z1 is equal to P2 by rho g plus V2 square by 2g plus Z2. Okay. The point 1 and 2 both are at the same datum. Both are sharing same datum. That's why what we can say, this point and this point are in a horizontal, in the same line. That's why I can say Z1 and equal to Z2. Z1 equal to Z2 means Z1 and Z2 cancels each other. They cancel. Then you will get P1 by rho g plus V1 square by 2g equal to P2 by rho g plus V2 square by 2g. Agree? Okay. Now the second case I will consider. This is the first case I considered. The second case I will consider. See, the second point is at atmosphere. There is no pressure, that is the water pressure on this point. We have atmospheric pressure. Always we have a tendency to assume atmospheric pressure 0 because all our pressures are gauge pressure. The benchmark is atmospheric pressure. Therefore, P2 becomes 0. Why P2 is 0? P2 is 0 because since P2 is atmospheric pressure. Right? Then your equation becomes what? P1 by rho g plus V1 square by 2g equal to V2 square by 2g. Agree? Okay. Second condition is over. Third condition I will consider. Now look at here. At a section 1, velocity V1, which is very small compared to the velocity at 2, one thing. Or you consider this section 1 where the water is still, or velocity I can assume to 0. Therefore, I am considering the section where velocity is equal to 0. Therefore, this term will go away. Then my expression becomes what? My expression becomes P1 by rho g equal to V2 square by 2g. Very interesting, right? Okay, now look at here. At this 1 point, I am considering the static pressure. Then the pressure at 1 can be written as rho g and water head or liquid head. This is the pressure at 1. Then I can write P1 by rho g is equal to capital H. Take this rho g this side. Then this one I will substitute in my equation. Then what happens? H is equal to V2 square by 2g. Then V2 square is equal to 2gh. Then V2 is equal to root 2gh. Okay. Now look at here. Here in this entire derivation or otherwise entire calculation determination, only one velocity will come in existence, that is V2. That's why I will just call it as a V only. I'll just call it as a V. V is equal to root 2gh. And this V determination we have done theoretically, therefore I can call it as a theoretical velocity. Our theoretical velocity derivation is complete. Now they are also asking us to derive an expression for discharge. Now what is the discharge? Theoretical discharge is equal to area of orifice into theoretical velocity. Okay, then area of orifice I can write it area as it is. Then theoretical velocity will be root 2gh. Therefore, you got an expression for theoretical. You got an expression for theoretical discharge. Thank you very much.